Okay, hi and good day everyone. So we continue our lecture on the topic of crosstalk control. Okay, crosstalk control is under deep submicron interconnect lah. Okay, so under crosstalk control, okay, we will discuss how do we reduce. Okay, how do we reduce the crosstalk? We cannot remove or eliminate the crosstalk, but we can reduce it. Okay. Actually, many ways to reduce it. Okay, we will look into detail for each of the way. Okay, and before that, I like to explain a bit on what is actually crosstalk, as to recap on what we discussed last week. Okay, I think we have the definition of crosstalk. Okay, okay. So crosstalk normally happen when what we call switching okay, switching happen in a wire. Okay? So that's due to the factor of capacitor. Okay, and the behavior of capacitor, you can see the symbol C here. The capacitor does not like to change its voltage instantaneously. Means that it wants to remain its current value of voltage. Okay, so voltage, what is the relationship between voltage and the switching? Okay, normally the switching, we have a voltage range to represent either logic 0 or logic 1. Okay, so to represent logic 0 and logic 1 in a digital system, normally we use certain level of voltage to classify between the 1 or 0. So for example, when we do a switching, okay, when the neighbor switch from 1 to 0 or 0 to 1, okay, what happens inside the wire? So the wire tend to do the switching too. The wire means that here the wire next to the switching wire. For example, we have this green wire and we have this yellow wire. So when this wire does switching, so the neighboring wire, which is the yellow wire, also tend to do the switching too. So this will actually give what they call as a crosstalk, okay, due to the capacitive coupling effect. Okay, recall back your course on related on capacitor. Okay, so when we have two conducting wires, okay, let's say here, and it has gap in between the two conducting wires, in this case air gap, so it will introduce a capacitor C. So this capacitor actually gives the capacitance or capacitive coupling effect, or the crosstalk issue or problem in our chip. Okay, so crosstalk is unwanted in our design, and but we cannot eliminate it 100%. Okay, we can only reduce the crosstalk. Okay, so to reduce the crosstalk, okay, so the effect of crosstalk you can see here lah, increase of delay, okay, and also gives the noise to the system or the chip. So to reduce the issue of the delay and noise, okay, so engineers, okay, produce or suggested many ways, okay, to control the crosstalk. And here is actually the listed main approaches used by them. Okay, first one, to increase the spacing between adjacent lines. So you have two wires, for example, to increase the space between the two wires. Okay, so this actually will reduce the effect of the crosstalk. Okay, and the next method, they will shield the wire. Okay, shield the wire with suitable shield material. Okay, to make sure that the switching from the first wire not affected the next wires or the neighboring wires. Okay, and another thing or another method used, they ensure that the neighbors switching at different time. So why at different time? So you go back to the MCF. So we have the MCF here, Miller coupling factor. Okay. When they do a switching at different time, okay, and then we can reduce the MCF. Okay. Okay. There is no effect at the neighboring wires. Okay. So if you do the switching at the same time for both wires, and then that will increase the effect of the crosstalk. Okay. And another techniques, okay, to overcome or to limit to reduce the crosstalk, they use the cancellation technique. Okay, cancellation technique, crosstalk cancellation technique. So lots of method lah, such as using wire arrangement, as mentioned in here. Okay, they mentioned 3 here. So this is just a point form for the way to control the crosstalk. So if you are asked to explain about way to control a crosstalk, don't just give point form of answer. If you just give point form of answer, you won't get the expected marks. Okay? To get the best, actually, you need to explain. Okay, the way to explain is must be based on your understand. To understand, you need to read the textbook. Okay, so from the textbook, okay, on page 232, okay, 232, the author of the book has suggested, okay, all of the mentioned crosstalk reduction technique, okay, which due to the capacitance inside the wire, okay, inside the chip. So normally for modern wires, okay, with aspect ratio, so remember AR, how do we calculate the AR? P over L, AR equal to thickness of the wire over width of the wire. How wide is the wire? So normally for the modern process, T over W equal to 2 or more than 2. And then the coupling capacitance can account for 2/3 or 3/4 of the total capacitance. And the crosstalk can create large amount of noise. So remember, so effect of crosstalk, it create noise to your chip or your system and also delay. Okay, remember these two. So that's actually the effect of crosstalk, which we don't want it to be in our chip. We want to reduce as much as possible the noise and delay in our chip. Okay, noise will cause our data will be corrupted. Okay, means that you do a processing. For example, you do an addition process, multiplication, or any complicated operation, and then you not get the expected output due to the noise. So in terms of design, yes, you did, simulation, behavioral simulation, everything perfect. But when you do when you come to the layout and also fabrication, and then you test it, your output is not as expected. So this is due to the noise and also to the delay variation. Okay, so that's actually angle that you can see from physical design point of view, okay, as compared to the front end point of view, design front end design. Okay. Right, so delay and noise are unwanted. So there are several approaches to control the crosstalk. So as I mentioned just now, so I give you time to read. Okay, you spend your time to read from this, okay, until before low swing signaling. So I give you time to read page 233, and then we will come back after a few minutes and discuss. Okay. All right, so hopefully every one of you get an idea. Okay, so what is actually happened here? So this paragraph explain a bit, okay, explain to you about so how do you increase spacing, okay, and about also shield wire and also ensure the neighbor switching at different time. Okay, so you just focus on the keyword so that you will get the idea on what is actually the paragraph is actually explained to you. Okay, for example, okay, the easiest approach to fix a minor crosstalk issue is to increase the spacing. Increase the spacing. So if the crosstalk is severe, okay, the spacing may have to be increased by more than one. This is depends on the situation. Okay, so increase the spacing as we discussed just now. So if we increase the spacing between the neighboring wires, and then the crosstalk issue will be reduced. Okay, depending on the severity, okay, severity of the crosstalk, right? If not severe, and then the noise within the noise margin or acceptable noise, and then the distance can be compromised. Okay, if the distance, if the noise beyond the noise margin means that it will affect your data, and then you will need to do more spacing. Okay, depending also on the size of the chip, right? So in such case, it is more efficient to shield. Okay, so normally for the case of the severe just now, okay, severe case, in terms of spacing, maybe not practical. Okay, not able to solve the severe issue of the crosstalk. So practically, normally, more efficient is to shield critical signal. Okay, so this is actually the next step to be considered by a designer. So they shield critical signal. So they identify what are those critical signal, okay, and then they shield that particular critical signal, okay, that particular critical signal or wire or bus, okay. So with power or ground wire on one or both sides to eliminate the coupling. So this is actually the method to reduce the effect of coupling. So they use the power and ground wires, okay, on the both side, on one or both side, okay, to eliminate. Another example, right? Clock. Okay, we know clock. We use the clock to, to all over our chip. Throughout our chip, we use clock. You recall back what you did in your lab. Okay, lab number 2. You did the what we call layout. Okay, automatic place and route, and then you see the clock there, and then how the clock reach at the element, clocking element. It's actually goes through a long interconnect. Okay, so to reduce the what we call effect of crosstalk, so normally clock wires, okay, wire that transmit the clock, okay, usually shielded so that the switching neighbors do not affect the delay. Okay, means that when the wire perform a switching, and then you have a wire that transfer the clock. Okay, for example, this is your global clock, GCLK, and then the clock travel, okay, they travel to throughout the chip, okay, and then what they do, actually they shield this. That is different color. They shield this wire, okay, to make sure that the clock is reduced in terms of the delay. Okay, so when the delay happen in the lots of delay happen in the clock wire that transmit the clock, and then they will introduce clock skew, higher clock skew. So that's actually the relationship between the crosstalk, clock skew. Okay, to make sure that our clock arrive at desired time or at least acceptable time, arrival time, right? So usually they shield the wires that for the clock, okay, and then that does not affect the delay of the clock wire and introduce the clock jitter. So another issue of clock is the clock jitter, okay. So that's why they shield that wire that the clock. Okay. Sensitive analog wires passing near digital signal should also be shielded. So analog wires that sensitive we also need to do a shield. Okay, to know detail about shield, okay, you can go to other references okay, and then you can explore further on shield process. Okay, how do people perform shield, wire shield? Okay, an alternative to shield is to this is another method. Okay, another method whereby designer interleave buses that guarantee to switch at different time. So remember we discussed about the switching. So we have two wires, for example, okay, wire number 1 and wire number 2. We ensure that wire number 1 not do the switching same as wire number 2. Okay, so that will reduce the crosstalk. Okay, so this is actually what people or designer perform So they interleave the buses, means that they do not put the buses that have the switching happen in at the same time. Okay, they interleave them. Okay, for example, so this they have that example. So if you are asked to explain, you need to give explanation this way You have an explanation with example. So that's actually give you a full mark normally. Okay, so if the example is clear enough, and then you will get full mark. Okay, if bus A, okay, so bus A, so we assume that this is bus A. Switches on rising edge of the clock, so rising edge of the clock, perform a switching operation. Okay. Of the clock, and bus B, okay, let's say this is B. Okay. And bus B, what happened? Bus B switches on the falling edge of the clock. Okay. Falling edge of the clock, which is this one. Okay, switching during this time. Okay. By interleaving the bus of the bits of the two buses, you can guarantee both neighbors are constant during the switching event. Means that we make sure that they are not switching at the same time, not during the rising edge of the clock. A and B not switching during the rising edge of the clock. That's actually what the paragraph trying to tell you. Okay, we switch at different time. For example, this is during the rising, and here you at the falling. So we can interleave this bus, right? So this avoid the delay impact of coupling. Okay? However, you must still ensure that the coupling noise does not exceed the noise budget or noise margin. That's what I mentioned to you. Okay? So the designer need also to know the noise budget. Okay? What is actually the maximum tolerable amount of noise for that particular design chip. Right? To know detail, you can explore further what is actually noise margin or noise budget. Okay? And how do people perform the shield. So what is actually important here that I want to explain here is actually we have the first one is actually we have spacing, increase the space. Okay. If the solution is not able to solve problem due to severe crosstalk, we can do the next step, shield critical signal. Okay. All right. And we have also another method, we do the bus interleave the buses, whereby we make sure that signal A and B, for example, not switching at the same time. They switch at different time, one during the rising edge, one during the falling edge, and then we can put the bus together. Also what we call as interleave bus. And I think that's all about the method. Okay, and number one, increase spacing, shield wire, and ensure the neighbors switching at different time. And we have also method on crosstalk cancellation. Okay, you can, I think, need to explore further. I think the crosstalk cancellation. Okay, all right. So you can read on your own on the crosstalk cancellation. Okay, I give you all. I think we also have group to present on this part. Okay, I leave you all to explore this and explain during the sharing session. Right. So we will go to the next chapter, which is on power. We will take 5 minutes break. And if you have any question, you may ask me during the break session or after we come back. Right? You can use the chat box as well. Okay. Thank you. All right, so we have come back, we continue. So before I forgot, so please fill in the attendance form. Okay, I already shared in the chat box. Okay, fill in, and then in the answer box, you respond the status of completion of your lab number 2. Right, so we continue to believe this is the last chapter of our course. Okay, low power design. Okay, why this topic is very important? I think all of you already understand what is actually low power. Okay, why you want it to be low as possible. So just imagine you have a device like your mobile phone. You don't want it to be to consume more power. Okay, you want it to be um, you only charge once a day. No need to charge multiple times a day. Okay, so if that's related to the power, okay, power consumption and power dissipation of that design or that chip. Okay, so in VLSI chip design, so low power design is one of the important element for the designer to consider. Okay, so nobody want to buy a chip that consume more power. Okay, we want to buy a chip that has a bigger functionality, complex functionality with low power consumption. Okay, so that's actually the what we call the aim of the uh, design, low power design. Right. So we will look into the introduction part of power and energy. So what is actually power, what is actually energy, and then how they're interrelated between each other, and then how they contribute to the dynamic power and also static power. Okay, so these two elements is actually contribute to the total power, okay, P total. Okay, total power of a design is actually combination of P static, okay, PS plus P dynamic. Okay, that's actually the element of the power, total power, P static plus P dynamic, whereby inside the P dynamic, we have the switching, P switching, PSW. Okay, then we will look into detail the effect of the switching to the total dynamic power. Okay, and then eventually to the total power. Okay, so from here to here, and then from here to the total power. So static power basically power that need to power up lah, your chip. Normally it's not consume more lah, okay, compared to the dynamic power. Okay, in terms of contribution to the total power, actually contribution most of the contribution comes from the dynamic element of the power, and most element inside the dynamic is come from the switching element inside the chip. Okay, so that is actually the general relationship between the switching power inside the dynamic element of the power and also the static power, and that these two contribute to the total power, okay, of our design. So let's have a look. We read this two paragraph. It's very good for everyone to know. So I give you time again to read and to have a brief understand on this before we discuss. Okay. Okay, we continue. So power can also be considered in active, standby, and sleep mode. So we have three types of power. Okay, active, standby, and also sleep mode. So what is actually active power? So active power is power that consumed while the chip is doing useful work. So this is actually normally during the switching activity. Okay, the activity of the circuit inside the chip. Okay, so it is usually dominated by P switching. So you can see here PSW or P switching contribute more power dominated by the P switching. Okay, standby power, or sometimes we call idle power. Okay, standby or idle power or static power normally not much lah consumed in the chip. Okay, if clock are stopped and ratio circuit are disabled, the standby power is set by leakage. So normally the standby power is determined by leakage power. So in sleep mode, okay, the supplies to unneeded circuit are turned off to eliminate leakage. So leakage is actually one of the element or the important what we call aspect need to be considered when we perform a design. Leakage is unwanted in our chip design. However, it still happen because of the practical approach, practical aspect of the chip. So we have a transistor, for example. We have a transistor here, for example, PMOS and NMOS transistor perform an inverter, for example. Okay, so this is your VDD, right? Then this is your ground. This is your input. Okay, and then you have the output here. Okay, so normally for an inverter to work, okay, either is the pull up element or pull down element. Okay, when they do switching, they will have a tendency of leaking a current okay, when the transition between the two transistors here. Okay, there will be a leaking current flows from the transistor goes down to the ground. So that's actually gives you one of example of the leakage current, okay, during the transition between the switching, okay, switching of the PMOS and NMOS. During the transition of the switching, it will introduce a leakage current. So that's an example of leakage. Okay. In sleep mode, okay, supplies to unneeded circuit are turned off. This we have discussed. Okay, this drastically reduces the sleep power required, but the chip requires time and energy to wake up. So sleeping is only viable if the chip is idle for a long time, or that's actually the situation where actually we need the sleep power. Okay, sleep power is not normally practical for application that we need to wake up what we call regularly. Okay, it's only practical for sleeping for a long time. Okay. Okay. So Gonzalez found that roughly 1/3 of the microprocessor power, so you can see here, okay, 1/3 of microprocessor power is spent on the clock. Okay, 1/3. Okay, 1/3 of the microprocessor power is spent on the clock element. So imagine how much the power is consumed from the clock. Okay. So another third on memories. Okay, memories is actually using a clock. Okay, switching, and the remaining third on the logic and the wires. So logic and the wires 1/3. So means that if we combine these two, it's contribute to the majority of the power come from the switching element because memory needs switching. Clocking element also needs switching. So remember we have discussed about 4 elements of clocking element: flip-flop, latches, memories, and also dynamic circuits. So those elements need switching. So that's why we can see here, it's mentioned here, most of the power is dominated by the switching power. Right, high-speed I/O contribute to a growing component too. Okay, for example, figure 5.6 here shows active power consumption on a processor. Okay, the core and other component collectively account for clock, logic and what. This is the statistic. Okay, statistics of in terms of the power. Okay, here we can see element of power as we discussed just now, power dissipation in the CMOS circuit. We have dynamic power and also static power. These two elements contribute to the total power, P total. Okay, P total. This is P dynamic and this is P static. So P dynamic, if we can expand it, okay, it comprises of charging and discharging of load capacitance as gate switch. Gate perform switching, and then there's actually a process of charging and discharging. And short circuit during PMOS and NMOS. This is what actually I mentioned here. Okay, here when PMOS and NMOS do a switching, and then there will be that what we call a short circuit current. Okay, short circuit current under the P short circuit. Okay, maybe I can zoom all. Okay, you can see are partially on. So it means that during the switching, transition of the switching is partially on. When it's partially on, current flows from the VDD goes to the ground, and this actually what we call as short circuit current. Okay, while both PMOS and NMOS taps on partially on. Okay, so that gives the dynamic element of the power, which is comprises of P switching and P short circuit. So if we can rewrite, the total power is equal to P static, okay, plus P P dynamic, which is comprises of P switching plus P short circuit as C. So these two is actually the dynamic power, PD. Okay, P dynamic, and this is actually P static. And elements of static power, we have 4 elements of static power. Okay, so static power comprises of sub-threshold leakage, so more on leakage lah. As you can see here, leakage, and also leakage. It's more on leakage. Okay, sub-threshold leakage, gate leakage current, junction leakage, and also contention current in ratio circuit. So these 4 elements, I sub is actually the sub-threshold, I gate leakage, I junction, and I contention give contribution to the static power. However, the element of the I here is actually is not much as the switching power. Okay, that's why the static power is normally P static. PS is less than the P dynamic lah. Lesser than the P dynamic. Okay, so the relationship between power and energy. Are you okay to proceed, or we can continue next week? Any response from the student? So no response, I assume okay lah, I proceed. Or we continue next week. Okay, no, clear, okay. Okay, to proceed, thank you, Anita. All right, so we have an element of power and energy. So what are the relationship between them? What is the relationship between power and energy? So power is drawn from voltage source attached to the VDD pin of a chip. Okay, so from the VDD pin, so recall back your lab, you have VDD and VSS. So VDD is actually the power, VSS is actually the ground. So VDD is actually used to power up your chip, or your to be specific, your circuit. Okay, to power up your circuit. So how do we power up the circuit? We supply VDD, okay, with certain amount of voltage as to represent either logic 1 or logic 0. Okay, that's actually will what we call introduce power as well. So we have elements of here instantaneous power. So instantaneous power compared to the capital P or P average here. So it depends on time. So that's why we call instantaneous. So P at time T equal to IDD. IDD is actually I from the VDD. Okay, IDD at time T multiply with VDD. So VDD is actually a constant. For example, we give a supply to our chip 3.5 volt, for example, 1.2 volt, for example. So that's actually the VDD is constant, but the current is not constant. Okay, the current depends on time t, and that's why the multiplication of the VDD with IDD at certain time give an instantaneous power P at time t lah. Right? So remember the equation P equal to IV. So that's actually the formula. P equal to I at time t multiplied with VDD. So we get the P at time t. Right. What's actually the relationship between power and energy? If we can make a what we call graph. So this is, for example, a graph. So this is T and this is P. Okay. So this is actually P at time t. We call as instantaneous power. P at time t. Okay, P at time t. All right. So we can see the pattern of the power is not constant lah. Normally it depends on the loading. So normally the power like this one. Okay. So how do we determine the energy? So the energy is actually the integration of power, instantaneous power from time 0 until time t. Okay, over dt. So that's actually we get the maybe I can share this is T. So the total area under this P instantaneous P is actually this is actually give you E. Okay, this give you E energy. Okay, so how do we get energy? So actually integration of PT okay over time t from time 0 until time t like this one. So this is what we substitute lah. PT ni we substitute with I VDD. That's why we get the I VDD. Okay, and then we get to get the average power. Okay, average power is defined by energy divided by T, which is maybe I can use different color. Okay, maybe this color. So to get the average power, this is actually E, the E divided by T. So this is E, we divide by T, and then we get the average power. Okay, average power. Right, to get the average power, we have E, which is IDD VDD divided by T. Okay. All right, so IDD VDD divided by T, we get the dynamic power. Okay, that's how we calculate the dynamic power. Okay, so what is actually dynamic power? Dynamic power is required to charge and discharge load capacitance when transistor perform switching. Okay, so this is the illustration. Okay, so this is the capacitor. Okay, and this is the what we call inverter gate. Okay, for example, so we supply the F switching. Okay, to the input, and then we will see the determine the dynamic power. Okay, so dynamic power, recall back the dynamic power is actually contribution from the P switching. Okay, P switching plus the P short circuits. Okay, PSC, and that's why we can see here FSW. So we want to estimate the P dynamic from the switching element. Okay. The explanation of this, I think we have in the textbook. You can explore further. So where we use the element of Q, okay, the charge Q equal to C VDD, remember, okay, and then from there you can substitute, okay, here, okay, C VDD, okay, C VDD equal to Q, okay, Q is actually we get from integration of the IDD over T. Okay, IDD over T, we get the Q, and also TSFW. Okay, TSFW is actually the factor of here. TSFW. Okay, right. The time multiplied with F switching. Okay, and then you substitute this. Okay, with the all of this, and then you get you can cancel them off. Okay, okay, and then you can also multiply VDD with the other VDD, get VDD power of 2, multiply with F switching, and then C at the front. So finally, we get P dynamic is equal to C VDD square F switching. Okay, C VDD square F switching. So from here, we can summarize that the more the value of the VDD, the higher the dynamic element or the dynamic power of the chip. Okay, how do we reduce the power, dynamic power? Any one of you can respond? What are the very important elements among the C, VDD, and also F switching? Which one is very important for us to tackle to reduce the dynamic power? Any of you can answer? Any? Any try? Don't worry, you can try. If you're not clear about the question, I can repeat. So we have dynamic power. Before dynamic power, we have equation of P total equal to P switching, sorry, P dynamic, please P static plus P dynamic, right? Okay, so we know that the P dynamic contribute more power to the P total, okay, dominant to the P total. And that's why we're interested to look into the dynamic power. So the dynamic power, we have derived it, so it's equal to CV square F switching. So among these three parameters, these three elements, C, VDD, and F, SW, so what are the very important elements that can reduce the dynamic power? Any try from you? So I give you time to think it, and then we can discuss. Okay, any try from any of you? What are the important elements to reduce the dynamic power? C, V, or F switching? Any answer? You look at the power. You see, VDD is a factor of 2. So any answer from you? Why? C. Okay, thank you, Haris. You answer C. Okay, any other try? Can use a chat box if you have problem with your microphone or unable to talk. You can use a chat box to respond. I'm able to see it. So one answer is C, mentioned about capacitance. Any other try? Don't worry to do mistake. Huh? Don't worry, it's okay. We learn together. C, okay. Any other try? The faster you respond, the faster we finish. Eh? We're about to finish the lecture. I'm looking for the answer. The answer is actually all of the element is very important. Okay, thank you, Haris, for the response. C, V, and F switching is very important to reduce the dynamic power. Okay, so but the most important or the higher weightage of the contribution is actually come from VDD. You see the factor of 2 here compared to others. Only one factor of 1. Means that if VDD is, we set it to 1 volt, okay, 1 volt, means that the factor of 2 is cancel off. Means that only the value of F switching and C multiplied by itself only. Okay, so that's one thing. And normally what people do is actually they increase the switching frequency because you want the our system to switch as fast as possible because we want the system uh, speed faster. Okay, computational speed faster computational speed. So when we want it to be faster, and the F switching will be bigger. So F switching bigger, and then the peak dynamic will be also bigger, and the total that the power dissipation also will be more. So that's actually the relationship between the switching frequency and also the dynamic. So there is a trade-off. You want the system to be faster than other system, and then you will sacrifice a bit in terms of the dynamic power dissipation. Okay. All right. So for the case of C, it depends on the area of your chip. If you want to reduce area, you want to make it smaller as possible, and then the more the dynamic power also will be more because of the effect of C inside the wiring inside the chip. Okay, I think that's all for today's lecture. We shall continue on activity factor next week because we almost end of our lecture for this week. Okay, we will do proceed on our lecture next week on activity factor. Right. So I will stop recording.